Hello and welcome to the unit on heat and thermodynamics, starting with Chapter 15, Temperature, Heat, and Expansion. Temperature is a quantity which you are probably more familiar with than just about any physical quantity, but it is hard to define what exactly it is. For now, we will define it as being related to the average kinetic energy of molecules or atoms. The kinetic energy of a single molecule or atom is found to be equal to the degrees of freedom divided by 2 times the Boltzmann constant times temperature, where the Boltzmann constant is just a constant which converts temperature to units of energy. It can also be argued pretty easily that temperature is already in units of energy. It's just in different units of energy than what we're used to. E is the degrees of freedom of the molecule, which for now is related to how much the molecule can move, whether or not it's a single atom that can only move forward, backwards, side to side, or up and down, or if it's a more complex molecule, which can additionally vibrate or rotate in place. Temperature in this case is relative to absolute zero, which is the temperature at which there would be no movement of the molecules and they would be frozen in place. I've said that temperature can be thought of as a different unit of energy, but in general, it is written instead in units of Celsius, Fahrenheit, or Kelvin. Celsius is a scale of temperature where 0 degrees Celsius is defined as the temperature where water will freeze, and 100 degrees Celsius is defined as the temperature where water will boil. Fahrenheit is probably the scale we're more used to in America, where 32 degrees is defined as the temperature where water will freeze, and about 212 degrees is going to be the temperature where water will boil. On the right, we see a conversion between Celsius and Fahrenheit in a thermometer. The difference between Celsius and Kelvin is adding about 273 to the degrees Celsius. So Kelvin starts out at absolute zero, and it turns out that the freezing point of water is about 273 degrees Celsius from absolute zero. Therefore, the Kelvin temperature is just going to be the Celsius temperature plus 273. Two objects are said to be in thermal equilibrium when they have the same temperature. When objects have different temperatures, energy will flow from the hotter object to the colder object until they have the same temperature. This transfer of energy is called heat, which is written as Q in our equations. The hotter object will lose the same amount of energy as the colder object gains, and therefore the final temperature is going to be somewhere between the two initial temperatures. The way that we calculate this final temperature is using the specific heat/heat capacity of the two objects. So how much temperature is changed by a given transfer of energy is related to the specific heat/heat capacity of the material. The energies lost or gained by a single atom or molecule is determined simply by its degrees of freedom. Heat is equal to the degrees of freedom over 2 times the Boltzmann constant times the change in temperature, where any molecule that has the same degrees of freedom as another molecule will take the same amount of heat to be raised by 1 degree Celsius or 1 degree Fahrenheit or 1 Kelvin. But the total energy change for a material made up of many atoms is determined by its heat capacity. Heat is equal to the heat capacity big C times the change in temperature, or by its specific heat. Heat is equal to the mass times the little c, the specific heat, times delta T, where little c, the specific heat, is the same for any type of the same material. So 2 kilograms of gold will take twice as much heat to raise 1 degree Celsius as 1 kilogram of gold, but they are going to have the same specific heat for the same material. Because all these different materials or different objects with the same different amounts of the same material or different materials with different amounts of different materials have different heat capacities, the final temperature of two objects placed into thermal contact is usually not exactly in the middle of the two initial temperatures. Another unit that we come across when talking about heat that we don't come across as often when talking about energy, even though it is a unit of energy, is a calorie. So 1 calorie with a little c is defined as the amount of heat necessary to raise the temperature of 1 gram of water by 1 degree Celsius. 1 calorie with a big C, which is also called a kilocalorie or a food calorie, is 1,000 times this. So it's the amount of temperature needed to raise 1 kilogram of water by 1 degree Celsius. The amount of calories in food is then determined by burning the food and finding the temperature that the flame raises a volume of water to. This is called calorimetry in honor of the units that it measures. There are many general rules for the interactions of heat with different materials, but water needs to be thought of in its own way because water is generally a special material. So water has a much higher heat capacity for storing energy than all but a few uncommon materials. Because of this, water is a very useful cooling agent in cooling systems of automobiles and other engines. And liquid of lower specific heat capacity were used in cooling systems. Its temperature would rise higher for a comparable absorption of heat. It is also useful in meteorology, where the winds in the latitudes of North America are westerly. On the west coast, air moves from the Pacific Ocean to the land, and on the east coast, air moves from the land to the Pacific Ocean. Because of water's high specific heat capacity, an ocean does not vary much in temperature from summer to winter. When you look at the Pacific Ocean versus the Atlantic Ocean, or San Francisco versus Washington, D.C., which are at about the same latitude, the Pacific Ocean will blow wind in and cool the temperatures in the summer or raise the temperatures in the winter, leading to a more temperate climate. Whereas in Washington, D.C., the air blows from the land to the sea, and you don't have this cooling effect or this warming effect, and you get much colder winters and much hotter summers. A general rule that is not 100% true for water, but is true for most substances, is that when the temperature of a substance is increased, its molecules or atoms jiggle faster and move farther apart on average. The result is an expansion of the substance. With few exceptions, all forms of matter, solids, liquids, gases, and plasmas, generally expand when they are heated and contract when they are cooled. An example of this is looking at a bridge like on the right-hand side, which is going to expand or contract depending on the temperature. What we do to account for this is place a grate which is able to come together or go farther apart depending on the temperature without decreasing the stability of the bridge or causing the bridge to collapse. Another thing to notice is that different materials respond to temperature changes by expanding at different rates. For example, brass is going to expand or contract more with varying temperatures than iron does. So if you place a strip of brass over a strip of iron and put ice over it, then the brass is going to contract more and bend down in the example that you see on the lower right-hand side. If you put a flame to it and raise the temperature, the brass is going to expand more than the iron, and the entire apparatus is going to bend up if you have the brass on top of the iron. This is a useful trick for thermostats, which allow us to see how much the brass and iron strips will warp at given temperatures and allow us to see the temperature without relying directly on a thermometer. A thermometer itself also uses this trick of thermal expansion, where you have a tube of glass filled with mercury. Mercury expands a lot with a little bit of a heat difference. As mercury expands, it goes up higher into the glass tube. And using markings and knowing how much mercury expands for a given change in temperature, we are able to know how much temperature has changed given that expansion and given how high up in the tube the mercury is. That said, water is a strange case. Liquid water is very dense compared to ice, which is strange and almost unheard of for most materials. This is because the electromagnetic hydrogen bonds in liquid water are stronger than the bonds that form when water is frozen and placed into a crystal structure. In general, the solid form of a material is denser than the liquid form, but in this case, it happens to be that the liquid water is denser than the ice. This causes interesting behavior where ice crystals in nearly frozen liquid water or water just above the freezing temperature are going to cause there to be a little bit less density than you would see with just purely liquid water. What this means is that up until about 4 degrees Celsius, instead of expanding its temperature goes up, water will instead contract and become more dense as the ice crystals melt into the more dense water. You see this curve in the bottom left-hand corner where the lowest volume of water is at about 4 degrees Celsius rather than 0 degrees Celsius. You also see the strange behavior where usually the solid will take up less space than the liquid, will take up less space than the gas. But in this case, looking at the upper right-hand corner, you see that the ice or the solid phase of water takes up more space than the liquid water and then jumps up quite suddenly when it starts boiling and when it starts becoming water vapor or the gas phase of water.